All right, this is Honors Algebra 2 Pre-Calc. We are doing 3.6, which is the last section in Chapter 3 of Algebra 2. We're going to talk about parametric equations on page 195 of your textbook. And I've cut a little bit of that stuff out of the textbook so that we can talk about it directly without having to handwrite all of it again. So, a small airplane takes off from a field. 1 second after takeoff, the airplane is 120 feet down the runway and 13.4 feet above it. The airplane's ascent continues at a constant rate. To analyze the position of the airplane as a function of time, you can represent the horizontal and vertical distances traveled in terms of a third variable, the time after takeoff. So this would be a parametric equation, right? So if we were going to use this exact setup, actually, right? So we could actually figure out that essentially my x of t, my horizontal position with respect to time, is 120 times t, and you can check that by plugging in the seconds, right? 1 second after takeoff, we have 120 as the x position, and then 2 seconds it's 240, which is 2 times 120, and 3 seconds it's 360, and 4 seconds it's 480, right? And y of t in this problem, right, the height of this thing, is a 13.4 times the number of seconds. So 13.4 times the number of seconds. So in general, a pair of parametric equations, and I do want to point out it doesn't have to be a pair. It's a pair here because we're talking only x and y, meaning left-right motion and up-down motion, and I'll explain what I mean by that in a minute. So a pair of parametric equations is a pair of continuous functions that define the x and y coordinates of a point in the coordinate plane in terms of a third variable, such as t for time, which is called the parameter, hence parametric equations. Now, the reason I mentioned that they say pair, but in the real world it's often more than a pair. If you picture a real airplane, right, a real airplane has to worry about left-right motion, which would be x, right, and up-down motion, right, up and down, which would be y, right? But it also would have to worry about motion in and out of the paper, essentially, in that third dimension, right? So we'll just say in/out, and that would be z. And actually, if you talk about real aircrafts and real, like, aircrafts both in space and also aircrafts, just regular airplanes, and things like helicopters, they also have other directions that you care about, such as like pitch and yaw, which is the way that these things like can rotate, right? An airplane can tilt, right? An airplane doesn't always look like it's flying straight ahead, right? Like so this is like an airplane from behind, right? That's if it's flying straight ahead. Well, the airplane could tilt so that its wings, so it's still flying in that same direction, but now it's tilted, right? And that's another direction the airplane can move, right? So again, when we talk about real motion, like in the real world, if you go work for NASA or like SpaceX, you're going to be worried about parametric equations in a lot of different directions, not just x and y. But that's kind of the idea behind parametric equations. So at this level, so let's talk about where we'll see them. So you're going to see parametric equations certainly in physics, right? You'll see it in BC Calc, so you actually won't see it with me in AB Calc next year. You'll see it the following year in BC Calc, which in college is frequently Calc 2, right? And you're going to see it in real-world applications, or if you go into any field that involves the way stuff moves, right? Whether it's ballistics, right? Ballistics is the study of projectiles, essentially. So ballistics, you'll hear that described on like the crime and lawyer and police shows because they're talking about bullets being fired, right? So ballistics is the study of how things fly through the air or are fired through the air specifically, right? Whether it's out of a cannon or a gun or a catapult or a trebuchet, right? It's the way things fly. So all of that's going to concern left-right motion and also up-down motion. And in some cases, it'll concern motion in and out of a space, like that would be the z-axis. But again, so real-world applications. Now that said, you're not going to have to do all of that in this class. So this is an introduction to parametric equations. We're not going to delve into all of the possible uses that we could have for parametric equations. We're gonna walk through some basic skills. So I need you to be able to do basically 3 things here. Number 1, graph a parametric system, including the direction of travel or the direction of motion, which we'll talk about in a sec, both by hand and on a calculator. So we'll walk through the calculator skills. We'll walk through how to do it by hand. Again, it's not going to be super duper awful. Skill number 2, eliminate the parameter to write an equation with only x's and y's. So that's going to be taking these equations and finding a way to write them only in terms of x and y. And lastly, use the previous 2 skills and a calculator to answer word problems involving parametric equations, which will be the most difficult of the 3, largely because I don't think that your book teaches it very well. So we're going to address that And again, this is something that's going to come up a lot more when you get to physics, right? But I want to make sure that you have a foundation, right? A lot of you in this class, not everybody, but a lot of you in this class are sophomores in high school, which means you're probably taking chemistry. So you won't have to worry about physics until next year, right? So, but I just want it on your radar that that's a thing that we're going to deal with. So let's walk through some parametric equations. So graph the pair of parametric equations from -3 to 3 for t values, and then they give us this. So here's the idea. What I want to do here is I want to make a table, right? So I'm going to make a table that has the t values that I was given. Now, if I wasn't given any t values, right? So I was given these, so that's what I'm going to plot. But if you're not given any, I would suggest that you pick -2 to 2 as a decent window. Or if it's a word problem where negative time doesn't make sense, because sometimes negative time doesn't make sense. In fact, here, time t equals 0 is takeoff. Negative time would not make sense. So if negative time doesn't make sense, then you would logically just pick like 0 through 5 or something like that. Okay, so I'm going to have a t value. I'm going to have x, which is apparently 2t minus 1, right? And I'm going to have my y, which is -t plus 2. Right? So I'm going to go ahead and put my t values. Right, so we'll go ahead and put our t values here. And then what's going to happen is I'm going to go ahead and plug in and find my x coordinate and my y coordinate, right? So again, I picked the t values I picked because they were given to me. I didn't pick decimals because why? The only time I would ever tell you that you have to pick decimals is if you're talking about a step function, which we did in section 2.6, I think. Anyway. All right, so when I plug -3 in, right, I'm going to get -6 minus 1, which is a -7, right? When I plug in -3 here, I'm going to get a 5, right? -7 comma 5, because the negative of the -3, right? When I plug in -2, I'm going to get -4 and a -1, so that's a -5. Plug in -2 here, and I'm going to get a 4, because it's +2 plus 2. -1 is going to give me a -3, right? -1 here is going to give me a 3. When I plug in 0, I'm going to get a -1 and a 2. And at this point, you can probably predict, because this is both of these are linear equations, right? You can see that these values are all decreasing, are all increasing by 2, and these values are all decreasing by 1. And so if you wanted to logically figure it out, you could go ahead and probably figure out the rest of the table without actually plugging in the values. It's up to you if you want to, but up to you. So now I end up with these points, right, with -7 comma 5 and -5 comma 4 and so on, right? So I didn't put an axis on here, which I should have, but I didn't, so here we are. So if I go ahead and make my axes, I notice that I need some negative y values, but not very many, but I definitely need negative x values. So 1, 2, 3, 4, 5 I always make bigger. 1, 2, there's my -7. 1, 2, 3, 4, 5 I always make bigger. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Great. Okay, so now if I plot my points, this is my starting point, right? This is my ending point. So I'm going to start at -7 comma 5, which is here. I'm just going to make a note that that's 1 in my own personal, like, whether you want to write a 1 or not is up to you, but I'm going to make a note that, hey, that's the starting point. -5 comma 4, right? -3 comma 3, -1 comma 2, 1 comma 1, 3 comma 0, 5 comma -1. That's the last point. So when I connect the dots, now notice they have closed dots because, so there's not arrows because I was given a stop point, right? Like this tells me to start and stop at these points. They're closed dots because they say equal to. And then what I pointed out in the original guidelines of what I wanted you to be able to do was to indicate the direction of motion. That literally just means, hey, put an arrow somewhere along the middle that says, hey, this is the way it was going, right? It started here, it ended here. That's all, right? So you don't have to, you can number it if you want, you could write start and end, but I want you to put an arrow to indicate the direction of motion, and that's the idea, right? And again, it would have been smarter if I had already put a grid on the paper, but I didn't, so here we are. Okay, so we're gonna go ahead and go to a, let's talk about how to graph this on the calculator before we go to P1. Okay, so in your calculator, if you press mode, you're gonna notice that there are 4 modes. There's function, parametric, polar, and sequential. Most of you are probably naturally in function mode because that's where most of us are all the time. But PAR, parametric, is going to be the one that we want to be in to graph these. Now, couple things. The other thing I want you to notice is this spot right here, the x comma t comma theta comma n button. Now that's your independent variable in whichever of these modes you're in. So if you're in function mode and you press this button, it's going to give you an x. If you're in parametric mode and you press this button, it'll give you a t. If you're in polar mode and you press this button, it gives you a theta. And if you're in sequence mode and you press this button, it gives you an n. So I'm going to go ahead and be in parametric mode. I go down to where it says par and I hit enter. Now, when you go to your y equals, you're going to see that it looks a little bit different. Your y equals now has both x1 and y1. That's going to be a pair, right? So here's my x1. It's 2. Notice to get t, I just press that independent variable button, minus 1, right? And then my y is going to be negative t. Again, I press that independent variable button, plus 2, right? So now, when I go to window, if you go to window, you don't want to mess with the t step, and I'll explain that in a sec, but you don't want to mess with t step. But what I do know is that I was given a t start, like a t min, a negative 3, and I was given a t max, which was a 3. And I'm going to explain to you what I mean by saying you don't want to mess with the t step in a minute. Now, if you want to adjust the window, the x's and y's, you can. This is the zoom standard window, which is the 10 by 10 by 10, but you can adjust it if you want. If I wanted to adjust it to make it look exactly like my window, I could. I'm not going to. So now when I hit graph, there's my graph, right? And it doesn't have it doesn't indicate the direction of travel, but what you'll notice is it graphed in that order, right? If you watch it as it graphs from here to here. So let me explain why I'm telling you not to screw with the t-step. Like, please don't mess with the t-step. Think about the t-step as taking pictures of motion, right? So if you think back to like making a flip book as a child, right, drawing pictures and then flipping through it and it makes it look like things are moving, right? Or if you think back to if you take a whole bunch of pictures, right? There's a reason that movies were essentially moving pictures, right? They're essentially still frames originally that were all like shot one after the other, and they're projected quickly, and then what ends up happening is it ends up looking like each of these pictures are so close together that they end up looking like moving pictures, right? So, and that's my terrible understanding of the original way that movies worked. Please don't quote me on any of that. So here's the idea. If you pick a t-step that's bigger, picture the t-step as when a photograph is being taken. When the photograph is taken, so let me inch this guy over for a sec here. Okay, so picture it this way. When the photo is taken, so you started at negative 3, right? And then another picture was taken at 0.13, etc. after that. So another picture was taken here, and another picture was taken here, and here, and here, and here, and here, and here. And that's how you get this nice, pretty line, okay? Now, because this is a linear function, right, because this is a line, it's actually not going to matter what your t-step is. If you made a t-step of 6 and jumped from here to here, it would actually still give you the same spot because it's a line. But if you have something that's curvy, right, so if we talk about something that's curving like this, right, that's a nice smooth parabola shape, well, if you have t-steps that's this 0.13 or something akin to that, right, you're going to get a nice smooth shape. But if you have a t-step where you only look here, and then here, and then here, and then here, what's going to happen is you're going to get something that looks choppy, right? It's going to have like these edges. Or if you had a t-step that was only here and here, it would look like a line, even though we know it's supposed to look like a parabola because it's jumping from here to here, right? So this t-step is telling your calculator when to take a picture and plot the result of that picture. So if you pick a really big t-step, you're going to get a really chunky graph. Now, I can't show you that with this current one particularly easily because it's linear. So what I'm going to do is I'm going to change this for a sec and pick something that's non-linear, okay? I'm going to change something and pick something non-linear to make the point that if I pick something non-linear and I don't go by a standard t-step, it's going to look gross. So let's do a t squared. Sure, we can do t squared. We'll just do t squared. Okay, so let's say I do this, right? And I graph this. Okay, so there's my graph. It's a parabola. If I now go to window, let's say I pick a really big t-step. Let's say I go by like 2s. When I graph this, it's going to look really chunky because it took a picture here and here and here and here. It missed the roundness of the parabola, right? It missed the curviness because the t-step was so big. So if I pick a bigger t-step, let's say I went by 5s. Actually, let's go by 6 because the distance is 6 entirely, right? So let's go by 6. If I go by 6, it's going to be a line between the two endpoints. That's it, because it only got a photo here and here. Even though we know it's supposed to go like this, it only took 2 photos and it connected the dots, right? So that's why you don't want to mess with the t-step. Now let's say I forget what the standard t-step is. I forget what it is, and I say, oh, I know it was something small. Let me put like a 0.01. Okay, I apologize in advance for what's about to happen because this is going to suck. Oh, okay, that wasn't too bad. Sorry, I take it back. Let's go back to window and pick something smaller. You got to go a little bit small to see this be awful. Okay. Okay, there we go. So that's a lot slower, right? You can see how it's more accurate, but it's really slow, right? So so the worst part here is if you do this and you accidentally type a really small t-step, or you do this to just mess with your friend, right? It's going to take. Oh, sorry, didn't mean to do that. Go to quit and then go to window. All right, t-step. Oh, my window range should work. That shouldn't make me quit. Hang on. I guess it won't let me pick a t-step that small. So that's good to know. Maybe the calculator has a plan in place now that won't let me do it. Anyway, so there's a small t-step. It's fine. The smaller the t-step, eventually what happens is you can see your calculator trying, and you watch your calculator struggling to plot this, and you're like, oh my goodness, why did I pick such a small t-step? So the point is, don't do that. This particular calculator is way more advanced than the actual hard real life calculator that I have from the 1990s, and it will allow me to pick a really small t-step, like 0.00001, and then it's just misery watching it graph. Maybe they've since built something into the programming so that you can't do that, which is nice of them. Now, let's say that you did all that, but you really wanted to get the original t-step back and you can't remember what it was. If you go to zoom and you hit 6, that's going to give you the standard window, which gives you the t-step of 0.13, etc., etc. But notice it changed my t's back to essentially 0 to 2 pi, which we'll talk about at some point and why it's 0 to 2 pi. But there's my window. Again, that's not this exact graph, but that's how you would graph things in parametric. Now, graphing things in parametric is great on a calculator, but it has some limitations, and we're going to talk about that when we get to the word problems. Okay, so moving on, you're going to try P1. I'd suggest you graph it by hand. You can also graph it on a calculator if you want. So I'm going to go ahead and graph this by hand. Oh, it's not an X, it's a T. Come on, brain. Sorry, guys. You know, you always put X on that side so many times for like decades of doing math that when it's a T, your brain just shuts down. Okay, so negative 2t plus 2, and my y is negative t minus 2. All right, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4. Ignore my terrible, terrible handwriting. Seriously tragic. They should not allow me to teach people with handwriting like this. Okay, cool. Anyway, so when I plug in negative 4 for t, I get a 10 here, right? When I plug in negative 4, I get 4 minus 2, which is 2. When I plug in negative 3 here, I get 6 plus 2, which is 8. When I plug in negative 3 here, I get 3 minus 2, which is 1. Right? When I plug in negative 2, I end up with 4 plus 2, which is 6. And so once you can start to see that this is linear and the pattern is that this is decreasing by 2, you probably finish this guy out, right? And you probably say, cool, I'm just not going to do all of that work. I'm just going to go ahead and figure out that that's what those numbers are. Same thing with this one. You're going to notice that it's decreasing by 1. And once you notice that it's linear and decreasing by 1, you're probably just going to fill out the rest of the table and not make yourself miserable. Cool. So it looks like I need some pretty big x values. I need to go up to 10 in x's and down as far as negative 6. And for the y's, I only need to go up to 2 and down as far as negative 6. So when I plot my points, I need 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Great. Okay. So notice that this is my first point, right? So 10, comma 2 is my first point. And again, it doesn't have to be perfect. I should have put a grid here, but didn't. 8, comma 1, 6, comma 0, 4, comma negative 1, 2, comma negative 2, 0, comma negative 3, negative 2, comma negative 4, negative 4, comma negative 5, and negative 6, comma negative 6, which is somewhere in that neighborhood. This was my first point, so when I connect my dots, which should be linear, right? I did a terrible job, but my arrow goes this way. And again, it doesn't have to be that big of an obnoxious arrow, but that's my arrow to say, hey, it goes this way. I didn't put it on the end because I'm not saying that this thing continues forever. I was just giving the direction of motion. And again, you can put that in your calculator if you want. If you choose to put it in your calculator, right, your your x1 rather is going to be negative 2t plus 2, and your y1 is going to be negative t minus 2. And when you go to your window, the only difference is you're going from negative 4 to 4, and then graphing. And there's your graph, right? So it looks the same, and there you have it. Okay, so let's talk about the next skill. So eliminating the parameter is a fancy way of saying write this as a single equation without t, or get rid of t, right? Because eliminate means get rid of, and the parameter is t. So to do this, what you're going to do is you're going to solve the easier equation for t, okay? So what this usually means is it's often the linear one. Now, your textbook is not going to give you any quadratics, I don't think, at this point, but I'm going to give you some quadratics because it's good for you to see. So it's often the linear one. Sometimes they're both easy and you just pick one. Then you're going to replace that t in the other equation with whatever stuff you got from step one. Now, this works in like 99% of the problems. Later on, when you know more stuff that you don't know now, including trigonometric functions, we're going to occasionally see a problem that has a trick in order to eliminate the parameter. But we don't know those things yet, so we can't do them yet. But when we get to them, I'll talk about it and we'll cross that bridge when we come to it. So let's go ahead and walk through an E2. So it doesn't really matter which of these two I solve for, right? So I'm going to pick this one because they're both linear. There's not one that's much easier than the others. So I'm going to say x equals 2t plus 4. So x minus 4 is 2t. So you can either do this as x minus 4 all over 2, or you could do it as a 1/2 x minus a 2, or you could do it as an x over 2 minus 2. I don't care. They're all the same thing. Okay? Any of those equal t. So then what I'm going to do is I'm going to take the second equation, and I'm going to say, oh, y is a 5 times the thing I defined as t minus a 2. So I don't care which one you pick, x minus 4 all over 2, great, totally fine, that answer's great. If you'd rather pick it as, if you wanted to pick a different one and distribute, that's also fine, I don't care. Less work is better than more work, right? So this is done. If you want to do more work, that's fine, right? It's not a hugely advantageous thing, but if you really wanted to, if you treated this as a 1/2 x minus 2, you could distribute the 5. You'd get a 5 halves x minus 10 minus 2. So you could also write this as a 5 halves x minus 12. That's also fine. Remember, the more work you do past an answer that was already correct, the more likely that you're going to take a right answer and turn it into a wrong answer by making a simple math mistake. So I'm just throwing that out there. You want to make fewer mistakes, not more mistakes, so don't do more work than you're asked to do. So again, I solved for one of them, whichever one I picked. I picked x in this case. Then I replaced all the t stuff in the second equation with that x stuff. If they're both linear, it doesn't matter which one you pick, since most of us feel more comfortable with our equations saying y equals anyway. I would say that was why I picked x in this circumstance, but again, sometimes one of them is much easier than the other. So let's try a P2, and then we're going to end this video, and then we'll do some slightly harder stuff. So again, here, it doesn't matter which one you solve for. Try P2, right? I'm going to pick x again, but you can do whichever one you want, right? So I'm going to pick x equals negative t minus 6. X plus 6 equals, sorry, I didn't say 2 before, equals negative 2t. So x plus 6 all over a negative 2 is my t, or you could make this a negative 1/2 x minus 3 if you like that better. It doesn't matter, right? Either way, you're going to take whatever you use for t and plug it in here, right? So I'm going to get that my y is, you're either going to write it as a 3 times this thing, minus 1, right? Or you might choose to write it as a 3 times this thing, which is also fine if you wanted it. So any of these are fine, right? If you want to distribute, you can make this a negative 3/2 x minus 9 minus 1, which is a negative 3/2 x minus 10. But again, if you were right and you add wrong, which I've done more than once in my life, like, so any of these are fine, right? They are all fine. You don't want to take a right answer and turn it into a wrong answer by making a silly mistake, right? And we've all been there, so I just want to throw that out there as a thing. Cool. So yeah, we're going to call that it for this video, and then we'll move forward after this.